Thank you very much. I would like, first of all, to thank the organizers for inviting me. It's a pleasure to be here in Helsinki and to participate in this very interesting conference. And so you see, I'm going to talk about machine learning for material discovery. So that's already my title, and it's also the topic of this workshop. And I'm going to present actually some recent work done in my group at the Research Center for Future Energy Materials and Systems in Bochum. So this, and in collaboration with Miguel Marques and this group at the same institute. And we are also there in Bochum, part of ICAMS, the Interdisciplinary Center for Advanced Materials Simulations. So we moved to Bochum last year, and these are really recent developments that, in the last months. And when I selected the topic, I thought that considering the audience of people working with machine learning, interested in machine learning, it was maybe good not to talk so much about applications for energies as we usually do in the institute, but a little bit more technical things maybe, and really some recent developments in the field of application of machine learning. So I will say something about the Alexandria database. That is a database that was, let's say, is curated by Miguel Marques in Bochum, and some features of the database, and also, hope to give you some ideas to use the database. And then this ML4MD that so we were talking before about descriptor. So this descriptor that we propose and that we use to interpret what is inside of Alexandria. And then we'll say something about universal force fields, because it's a very interesting topic at the moment, and in particular benchmarks for phonons. Yeah, but first of all, little motivation, and I like to ask this question because depending on the audience, I get very different replies. So we know, why do we need to discover new materials? So this is the question. And we know that all technological items, that so for example, a mobile phone or smartphone that we all have in our pockets are made of materials, some crystalline, some not. I will mainly talk about functional crystalline materials. But the question is, how many chemical elements are contained in the materials that make a mobile phone? Can you guess the number? How many different chemical elements in an average smartphone? 20? Okay, someone wants to offer more? Less? 50? We have a 50 there. Nobody dares to offer more? Okay, you're rather conservative. So actually there are 70, and so at least 70. Then of course depends also on the specific model, including 8 rare earths. So basically, if you consider that there are 83 stable non-radioactive chemical elements, this means more than 80% of the chemical elements used in the different components, different parts, but especially for the functionality, there are some chemical elements that are considered critical, like for example rare earths, that are essential to make function the vibrating parts, or to make function the screen, the bright colors of the screen, etc. So, of course, we have to consider that we are looking for new materials, and we have a finite number of chemical elements, but many ways to combine them. And this makes that the search, just a combinatorial search, is going just to be impossible. So, of course, we want to accelerate, thanks to machine learning, the data-driven approaches, the search of new materials. And of course, we also want materials that can be used for a specific functionality. So we are not just looking for new materials. We have some performance requirements, and we want then to target our search to go in the right direction to find the materials we are interested in. And at the same time, we would like also to impose some constraints. So, for example, of availability of chemical elements and sustainability of the process to extract or to mine these chemical elements. So there are several constraints that cannot be just forgotten, because we cannot forget that indeed the chemical elements, some of them are critical. So this is a well-known problem, not only geological, but also political. So you can see here the periodic table that is every year published by the European Chemistry Society. And the different size of the cases of the squares of this table is now deformed to represent the availability of the chemical elements. So a big case would mean that it's more available, but also the colors give us some information. So green is nice, it's plenty supply, no problems. But if we go to yellow, orange, and red, we are getting to some elements that are threatened, maybe not available. Or of course, we cannot just develop a new technology based on critical elements. So here you see also the most common elements in the mobile phone. So these are about, so really the most common. There are many more. So we have to keep in mind this picture and now try to use what we have, the computational tool we have, to work to have new materials possibly in a sustainable way. And sustainability means also to reuse the calculations that we have already made. So materials databases are very important because we use a lot of energy also to do calculations. So it would be very stupid to keep recalculating over and over again the same thing. We need to be able to use the data and to share the data. So this is another very important topic. And so this leads me to the Alexandria Materials database, and I will tell you something about the database. So it's hosted in Bochum on our servers, but is now available since a couple of months also in Nomad. So I actually think it's still in the developer version, but it will be soon available for everybody. They are preparing some nice tutorial, the FEMAT team, to be able to already learn how to use in Nomad the Alexandria database. So it's about 5 million compounds. There are many more calculations because there are, for example, structural relaxations, etc. So there are million of calculations, but for about 5 million crystalline compounds. The calculations are done with VASP, all of them, and using different exchange correlation function, but most of the database is about PBE calculation for compatibility with other application and databases. There is an Optimade interface as well, and there are not only 3D materials, but also sub-databases of 2D, 1D material, and now we are also inserting 0D, so inorganic materials. Of course, it's free, so everybody can get it and access and use. It's ready to be used for machine learning. Now, the history of how this database was built. So it started with high throughput calculations for a family of materials. We started with perovskites, and then we went on. We added other families, other prototypes. Then we combined this prototype search with crystal structure prediction. So this brought more and more compounds that were kept being stored in the database. So we included what was in the materials project database. We started to do some further prediction using machine learning as soon as database was large enough to predict new stable compounds. Because if you look at the distribution of materials as a function of the distance to the convex hull, that I will show you now, measure the stability. So most of the materials are unstable. So there is a big peak at 0 that are the material on the hull that are stable, but most of the materials in the database are anyway unstable. And so these are different phases in which we increase the size of the database. So now at the moment there are in Miguel's group generative models to find new structures that can be stable, not only 3D, but also 2D, 1D. So these things keep going, and the database keeps growing. And I just want to show you this example here on chemical similarity. This is a work of a few years ago, because I will use then this chemical similarity later for the descriptor. And this was a time where the database could grow a lot. And we simply use this concept of data mined similarity to predict compounds that were more likely to be stable. How does it work? So chemical similarity, it means, so we build a matrix of similarity just using data in experimental databases. So looking if it was possible, given a certain crystal structure with a certain composition, just to replace one chemical element with another and still get a material that was stable, still in the experimental database, so experimentally stable. So in that case, we would say that these two elements that can be replaced are chemically similar. And build then a matrix, okay, where we have the periodic table on the x and y axis, and off diagonal terms will be non-zero if we can substitute one element with the other, and actually counting how many different structures allowed replacing one element with another will give us then a measure of this replaceability. And on the diagonal, we put the number of compounds, crystalline compounds that are in the experimental database with a certain chemical element. Then renormalizing this thing, one gets on the off-diagonal elements a measure of replaceability of a chemical element with another from 0 to 1. And this we used to predict convenient structures, starting from the known experimental structures in different states. So we did several iterations of that, and then did the DFT calculation to check if it was really stable, and increased in this way the database Alexandria. At that time, it was not called Alexandria yet. And the success rate with this kind of procedure was quite high. So this concept of chemical similarity is something that is rather powerful. And so that's why then we use it further for a descriptor. So all the calculations in the database Alexandria are done with density functional theory. And as I told you, we used different functionals, still relatively cheap functional to perform many calculations. And what we want to determine in the end is the convex hull of Alexandria, so of all crystalline compounds. So I need to define the convex hull in case someone didn't know yet what it is. So if you have the formation energy, so we are working at zero temperature, so ambient pressure, and of course this is what is done for the calculation of Alexandria, but this could be generalized, of course, including effect of temperature. We have the formation energy then as a function of the composition, and in 2D with two chemical elements that can be mixed to make compounds, it's rather simple. We have some stable phases that are here with these green dots, and these lines compose the convex hull. And it's something now like tin chloride is above the convex hull. This distance here, the distance to the convex hull, is a measure of instability. This means that the higher this energy is, the more unlikely it will be that the material can be stabilized, knowing that there is anyway error in the approximations in the calculations, and that we are at zero temperature. So this thing would decompose in tin and tin chloride too. So we can in this way build for all binary compounds, but also for ternary compounds, similar things with the color map is still easy to visualize. What are the compounds on the crystalline compounds on the convex hull? But when we go then at higher dimension, we can make quaternary, quinquenary, multinary compounds. Then the situation becomes harder to visualize, and still it's something that we can calculate. We can build the full convex hull for all the 89 chemical elements that are in the Alexandria database. And so that's what we have done. It's a thing that is, of course, not so easy then to analyze, at least visually. So you can see here that in the experimental database, there are a few thousands of stable compounds. If we get rid of alloys or things that are not fully crystalline or fully defined. In the Alexandria database, we have now 250,000 stable compounds on the convex hull. And this is the GNOME database, so the published in 2023 by Google DeepMind. So of course it's larger, but so we know what is in the convex hull because it was kind of published, but we don't know their full database, and these things cannot really be used, right? Because they are distributed with a strange license. So overall, the Alexandria database is the open database with the largest number of crystalline compounds that is available for computational study. And just a last slide where I want to show something about the distribution of the materials properties in Alexandria, because some things are not, so now that we have all these materials, we can look how they look like and what are the different properties. So for example, most of the material are metallic. So if you look at the gap distribution, you wouldn't even probably see this orange line because here it grows a lot. So there are a lot of metals, and then the gap decays very, very, very quickly. So in general, when we have distributions that are so strange, so far from a normal distribution, it will be also difficult to use this data to do machine learning prediction. So usually the more, so the nicer is the distribution, like for example, this formation energy distribution is relatively nice, then it will be easier to train a machine learning model. So the statistical distribution have anyway some importance. And yeah, I'm stuck. Oh, okay, thank you. And so, for example, now I use, I try to predict these properties, of which I give the distribution with a compositional model, CrabNet. So in this case, we just give the chemical composition as an input. And one can see that there are some properties that converge very, very easily and quickly. So the MAE will be immediately very small, and there are some properties like the band gap that struggle to converge, and one needs a very, very large data set to get converged result. So, but in general, when we have a large data set, large enough, so this is the order of million data points, one can converge basically everything. I could say more about the applications that we did in machine learning with Alexandria, but I wanted to present another thing. So this Pettifor embedding that we have developed, because it's a nice example of a descriptor that is data mined, is efficient for machine learning applications, and it's easy to interpret for us, for a human. And it's based on this concept of chemical similarity that was in this article of 2021. So here, if you can of course get this embedding, there is also a notebook to use it with Alexandria to see how it works. But okay, I tell you first what it is. So it's an embedding for chemical composition, then can be combined with an embedding for the structure, crystalline structure. But for the chemical composition, now the idea is to use this concept of chemical similarity. And so let's start with a possible representation for a compound like K2O or rubidium to oxygen. We can use just an orthogonal representation. So we would have an 89-dimensional space. In this case, okay, I have a small representation in just in 3D for these three elements that are involved. It means that the coordinates would be 0 for the other chemical elements that are not involved in the compounds. And we just use a move of 2 steps in the rubidium axis, 1 step in the oxygen axis. We have this vector that represents the rubidium oxide. Similarly for potassium oxide, and now we renormalize everything in such a way that these vectors are on a unitary surface, and this would be our representation. Now, this representation has some drawbacks that I will show soon in the next slides. We modified it using the chemical similarity in such a way that the axes are no more orthogonal. And this angle here, so the cosinus of theta, is equal to the similarity index that we have built with the similarity matrix. So it means that if the chemical elements are very dissimilar, the similarity will be 1. And in that case, the two axes, the similarity will be 0. And in this case, the cosinus of theta will just be 90 degrees, and the axis would be again orthogonal. But if the two chemical elements are similar, then this angle is smaller and gets smaller and smaller the more similar the chemical elements, never getting really equal to 0. So we will always have an 89-dimensional space. But we can get then that these two compounds are closer in this representation than in this. So we can define the distance of the chemical compounds based on similarity. And this distance, we can use it to, for example, to measure things. This is just an example, simple example with element, chemical element, but we can do the same thing with the compounds. So you see now, we compare different distances that were proposed. So for example, these two here on top are also based on the concept of chemical similarity, our chemical similarity, but they use some Earth mover distance instead of Euclidean distances. We use in our Petit-4 scale this distance concept that I've just presented, and these are just using different representation, different embeddings, like Mat2Vec that comes from text mining, or MagPi that is just made of vector of elemental properties. And we ask ourselves, what is the closest chemical element to sulfur? And the answer that we get is selenium, then we have polonium and tellurium. Then the different embedding would give different answers. For silicon, we find germanium, tin, gallium. So we find in general, so these embeddings that are based on chemical similarity give very, very similar answers. And then we can then plot, kind of using this concept of distance, plot a map of chemical elements. It would be kind of a data-mined periodic table using UMAP for dimensionality reduction. So you can see here that, of course, clustering is due to the fact that some chemical elements are closer according to our concept of distance. And you can see that here the different groups in the periodic table that they really tend to cluster in our representation. And this thing is in comparison what one would get with the one-hot representation that I shown at the beginning, just with orthogonal axis. So here there is no clustering at all because there was no information on similarity between the different chemical elements when we built that representation. If you use this Mat2Vec embedding to do the same dimensionality reduction, you still can find some clustering, but it's not so well defined as with our embedding, or with MagPi. Again, it's much better. So it uses elementary properties and it's much closer, but still, okay, it's not perfect clustering. And then we can apply it to families of materials in our Alexandria database. For example, perovskites. So the structure is fixed, so we are just using the composition embedding. And of course, there are all these different clusters that contain basically, if you zoom in, they will have the same anion, these different kind of regions that are formed. And then we can also see that, so for these are with transition metals for A and X, the biggest islands, and then the smaller islands are with other compositions. So we can have a map of the different families, but we can also use our embedding in graph neural networks, just use them as embedding of the elemental species on the nodes of the graph. So this we also used it in compositional models, tested on many different benchmarking different data sets from few hundred to 100,000 data points, and it seems to work quite well. And then if we combine it with a structural embedding, so we use the one of the materials project, what we obtain is interesting representation of Alexandria convex hull. So here we project it on different families of prototype of crystal structures. Or we can separate metal and non-metals, and you can see that there is a very clear separation. But there are, on the other end, other properties that don't allow to get a very clear separation. So this is, okay, interesting is also due to the fact that we have always problem with magnetic materials when we do calculations with VASP, and we only consider ferromagnetic ground states. So many things that are antiferromagnets in our database are ferromagnets. So this is a thing that maybe has to be then reconsidered, but it will take time. And still we can see that machine learning kind of understand that we have problem with magnetic compounds, and here is not able to distinguish. And then we can also look at the two different, we can try to ask, how do we find a material with a similar band structure to another one? Just looking at the distance in Alexandria convex hull. For example, is there a material with a similar band structure to diamond silicon? So what is closest to silicon according to our metrics? And we get germanium and silicon carbide, but also some compounds like this one, nickel, silicon 3, potassium 4, phosphorus 4, that is rather close, and we can compare the band structure. Orange is silicon unfolded in the Brillouin zone of this compound, and blue, the band structure of this compound. That, okay, wouldn't have been so obvious to guess, and just by chemical similarity, we get some property similarity, so we can access also information on the properties. Okay, just would like then to move to the third topic, but this will be faster. So the force fields, so we have a lot of data, so we also like to do benchmarks of different things. And in the case of universal force fields, there is a benchmark that is available for everybody, is updated regularly, many things. So I have updated it yesterday, this figure for the presentation, because I gave it 2 weeks ago and it was already different. It had already changed. You see many things that just come out very, very quickly. And so this is the MathBench Discovery Leaderboard, and you see the different the foundation model, the difference of universal force fields. You can also click here and see who has developed them, and you have information also on, you can get the model, have information on the theory paper associated and everything. How many parameters are included in the machine learning model, and also here which is the data set that has been used for training. And Alexandria, so, or subsampled Alexandria is used, so subsampled because we have to remove, so it has been removed what is this database that was the original database from chemical similarity paper that is used for the test of all this MathBench discovery. So of course this data shouldn't be used in the training of the machine learning force field. And so you see that ICAMS is also a part of this. So a group of Ralph Trautz at ICAMS develops a universal force field. So now we benchmark the phonon properties, building a data set of phonon calculations with PBE. There was available a data set of phonon calculation with PBSol, this MDR data set. But okay, of course, if we want to compare with the force fields that are trained on a PBE database, it is not really convenient to use PBSol phonons. And so you see also here a comparison of what would be this distribution of phonon frequencies with the PBSol, so that are always at a higher frequency than the PBE phonons, for example. It gives you also an idea of the error that comes from having different, use different functionals. And then, so this is in the article that is in the archive, submitted some months ago, still not published. But meanwhile, there were many other force fields coming out, so we have updated the result. So this is the error of maximum phonon frequency. And this model here from Meta And the orb force field were the best on the leaderboard when we did this first benchmark. And they gave very, very bad phonons. They're still here, you see very bad phonons. But meanwhile, they made more, so they updated their models. So now there is a new orb with better phonons that are actually, yeah, so it's still not here. So it has came out very recently, but we are testing that also now. And there is also a new model of meta that solves this problem. So the problem with the phonons here come from the fact that these two models are non-conservative. So the energies and the forces are predicted separately. They are not a derivative. So the forces are not derivative of the energy. And so in this way, the models can be faster because they have more flexibility. They have also a lot of parameters. But when it comes to phonons, the potential energy surface is noisy. So it has some high frequencies noise. And so it's very bad to calculate phonons. And very often the calculations don't even converge. So we checked also many other properties related to phonons, vibrational entropy, free energy, heat capacity. So, and one can see that there are some force fields, in particular Mattersim from Microsoft and these Grace force fields that work extremely well, have errors that are much smaller than the difference between PBE and the PB-SOL. So our conclusion is that the force fields, universal force fields, can already be used as they are just to calculate very, very reliable phonon and phonon-related properties. And this was not the case until just last year. It's a very new development. So this is just a table with the final results, with really the numbers of the different errors. And yeah, so I would like just to conclude with the Alexandria database. Again, a map with the different crystal systems in Alexandria. So it's an open database and it's growing. So we keep working on adding new materials and also more diversity in terms of dimensionality, whatever, new functionals. Because then the next step is maybe to improve the quality of the data. We have enough data to have a very good predictive model. So in our field, the big data is maybe not so big as in other fields, but when one has millions of data points, can do very, very interesting things. And I would like to thank my group, Miguel Marques, of course, and his group here in Bochum, and the funding agencies that are supporting my group. And I'll leave you with the QR codes of Alexandria and the Petit for embedding. And we hope that you can find these developments useful for your work also. And thank you for your attention.
Thank you very much for a very interesting talk. Are there any questions from the audience?
Yes, thank you for the presentation. I have a question about Petit for embedding and clustering into metals and non-metals. So it seemed from the Petit for embedding that it does not inherently kind of have some features that would distinguish between metallic and non-metallic species. I wonder how then it occurs that you separate on the 2D plot that you separate metals from non-metals. Maybe if you can comment, like, what is the kind of idea here, or
yeah. So okay, so we did also some PCA analysis. Wait, where was this? Because it's not so obvious now from this UMAP maps to understand what this means in terms. So we found that there are some 6 or 7 descriptors, or properties that are very strongly correlated with, for example, with this metal non-metal. So if we go inside the analysis, then we can try to understand a little bit better what correlates with the different maps. Not directly from here, right? So here is more a representation, and it's more in terms of distance. So kind of if we stay closer to a metallic element or metallic compound, we are likely to find another metallic compound according to our distance definition. But then here the separation is yeah, you see still some things that are intermixed. So it's not enough just to say metal or non-metal with the predictive power. Yeah. It's more qualitative, more for the understanding. Then, of course, you can train a machine that will use this as an input and will tell you metal, non-metal. So that will work quite well.
Thank you.
Thank you again for really nice talk. Lots of very interesting things. I want to ask more questions, but I'll ask about the stability study, the one you showed in the earlier stages. So I maybe missed what kind of descriptor you were using to predict the stability. Was it just the name of the compound, or was it some kind of numerical similarity measure?
So we have different machines to predict stability. We have tried several things.
Right.
So, okay. And yeah, so the thing that we used the most, it was this graph neural network. So in that case, we input information on the composition and on the crystal structure, the order of neighbors, the coordination, if you want. And from that, we get output, is it going to be stable or not? We have also tested some purely compositional models, but then you cannot distinguish between the different polytypes. So it's obviously annoying. So at the moment, what we do the most is to combine some machine learning force field to get a geometry quickly, and then to go through this graph network and predict stability. This works with errors of the order of 10 millielectron volts per atom. And this it was very, very sensitive to the how biased is your database, let's say, because at the beginning we started with families of crystal structures. So for example, to predict a perovskite, we had super small errors, and to predict other crystal structure like a monoclinic, it was a very big error. And then we worked a lot in making more uniform the database from
Very useful. Thank you.
Again, thank you for that lovely talk. I also had a question on the stability when you're looking at replacing atoms based on chemical similarity. I think you mentioned that there was a 10% success rate based on sort of whether or not those structures were found in the literature. And I was wondering if you had thought about the issue of perhaps synthesizability, that perhaps these compounds are indeed stable, it's just no one has made them yet. Thank you.
Thank you very much. Maybe one last question.
Thank you for a great talk. I don't know much about material science, but from the deep learning perspective, for example, how did you choose the parameters of the UMAP, the number of neighbors, the minimum distance, and the epsilon parameter? And for example, in the graph neural network, how did you build the adjacency matrix? Is it symmetric, upper triangular? How is it built? So in this way, you introduce structural features to the. Okay, thank you. Thank you.
Thank you again for the talk. And I know there are lots of questions, but I guess there will be some time, yes, after. So now